So we're starting by trying to figure out how do we know these values without a calculator. Now, hopefully, I bet you got at least one of them, right?
I got two of them. 2.5.
The middle one, obviously, we can do without a calculator, right? But what about the square root of 3.9? Do you know what that is without a calculator?
1.7.
Well, it's going to be a decimal, obviously, because it's not a whole number.
1.95.
So then we need to be able to try to figure it out. Now, of course, we can know some things. We can know that it's going to be just a little bit less than 2 for this one. Or for the 4.1, we know that's going to be just over 2. But how much? You know, if we wanted to figure out how much that is, like 3.9, is that going to be 1.9? No. Is it going to be closer to 1.95? What's it closer to? And we want to be able to figure that out. And one of the cool things is that actually our calculus skills are going to allow us to come up with ways to know this. Now, I will say, though, that all of the methods that we're going to be looking at, though, they're going to be approximation methods. They let us get really, really close. But they may not necessarily be exact values. But certainly that's a lot better than trying to do these square roots by hand. So, first up, some notes.
Right.
We're going to be looking at linearizations today. So add this into your notes, please. All right, so hopefully by now you got all this in your notes. Now, a couple little details, making sure you see these out of the notes you just took down. First of all, notice it starts with L of x. The linearization is represented as L of x, but L of x is the equation of a line that's tangent to our curve. And so because of that, it always has to be tangent at a particular point. The point is defined as having an x value of a, therefore the y-coordinate is f of a. Because, of course, you would plug the a value in to figure out what the y-coordinate is. Now, this tells us approximate values as we go and use this. Now, notice, though, it's for f of x values of x that are close to a. So this approximation works as long as we're looking at something close to the point, but not nearly as well if we're looking a long ways away from the point. And we'll see some graphs to see why that is. And yes, it does go by another couple names because this process is called linear approximation or tangent line approximation. So we're going to be practicing it with the same problems that we were looking at the start of class. Now we already knew one of them, but we want to be able to approximate the other two, the square root of 3.9 and the square root of 4.1. Now, what a value am I going to want to use if these are the numbers I'm looking for? I want it to be something close to the 3.9 and the 4.1, so yes, I want the a value to be 4. And so that's the number that we're going to be using here. Now, the first step for finding the linear approximation, remember it was also called a tangent line approximation, is we're going to figure out what the equation is of the tangent line at 4. Well, of course, in order to find the tangent, the first thing we need to do is we need to find the slope of the tangent line at 4. So please find f prime of 4 for this particular equation. All right, so to figure this out, we're finding out what f prime of x is first. We got to start with the actual function. We can't just plug the 4 in at the start, otherwise everything would be 0. And so I want to find the derivative of square root of x. Remember, square root of x, the square root of x is the same as x to the power of 1/2. And so I can just use power rule with this one. So I end up multiplying by the original exponent, so I multiply by 1/2. And then, of course, we subtract 1 from our exponent. That's going to be x to the power of negative 1/2. And then, let's just clean that up a little bit. Remember, that is 1 over 2 root x. So that's my derivative. So if I want to know what f prime of 4 is, I plug the 4 in there. So it's going to be 1 over 2 root 4. What does that equal?
1 over 4.
Yep, 1/4. Because the square root of 4, of course, is 2. 1 over 2 times 2 is 1 over 4. Which means that if I'm going to write the equation of that, then I know that I'm going to be doing 1/4 x plus b. I still got to find out what the y-intercept is. So, remember how we find the y-intercept in our equation? I can actually take the coordinates of a point and plug them in for x and y. Well, as I look at this one, of course, it's going to be 1/4 times the x value. Well, that's the a value in this case, so that's 4. plus b. That's what I'm going to find. But what is the y-coordinate here? Well, we'd actually have to figure that out. What is f of 4? In other words, the square root of 4.
2.
2. So the y-coordinate is 2 at that point. All right, we can now solve that to figure out what b is. So first thing I do is 1/4 times 4, which is 1. And then I can go ahead and subtract the 1 from both sides. We end up with 1 equals b. And so now we know that the equation of the tangent line at 4 is 1/4 x plus 1. But you'll notice I didn't just write y equals now, because I'm going to be using this as a linearization. Really all linearization means is equation of the tangent line at this particular point. It's just being able to utilize it in a particular way. So make sure that you have the L of x equals with your equation there. All right, so now that we know what L of x is, we can now use that to approximate our two values. Because remember, we're doing that just so we can figure out those. So for the first one, I then want to figure out what is L of 3.9. So we're going to do 1/4 of 3.9 plus 1. And so if we do that calculation though, well, we still got to do 1/4 of 3.9. That's not super easy. But it is 0.975.
Wait, are you not allowed to?
And so we're going to do plus 1 with that. And so in the end then I can figure out that L of 3.9 is 1.975. All right, now if you want to compare this to the actual number, if you did this on your calculator, the number that you would have gotten is about 1.9748, and it just keeps on going and going.
That's the...
So you'll notice it gave us a very close number. So while we could say earlier, I know it's less than 2, but I couldn't necessarily say by how much. This gave us a very good estimate. It got us very, very close to it. So that's pretty good. Repeat the process, please. Take a moment. Figure out what is L of 4.1 going to equal. So find that estimate, please. So when we do this calculation, we plug in the 4.1, and we end up getting 1.025 plus 1, so it ends up giving an estimate of about 2.025. Again, a very close estimate of the actual value. Now, do you know why the tangent line would give us such a close approximation? Well, let's take a look at the graph of this, because it's good to actually be able to see it in it. So here's our graph of the original function, and we're trying to figure out what's going on at 4 there. And so the original points that we're talking about here are like 3.9 and 4.1. They're close to that, right? Well, if I take a look at where the tangent line is, notice that's very close to my graph here. In fact, if I zoom in a bit, we can see down here that if I zoom way in on that graph, the tangent line is very, very, very close to the curve. Because it's like if you're playing on your graphing calculator and you zoom way, way in on the curve. Eventually it looks like a line, right? It's not a line, but it's just curving so slowly by the time you zoomed in that you can't really tell. The same thing is happening here. So we're finding the tangent line because that gives us something that's following right along that graph, really close to it. But it's much easier to calculate these linear values than it is some of these other crazy values. And we can actually do this with all sorts of function types. All right, now a couple other little things to notice here. Remember, I use this for values that are close to A. Notice if I went a ways away from A, it'd be a lot less useful. So it really is an accurate description the closer and closer we are to our original A value. Also remember, this was the demonstration for one particular A. This was for just A equals 4. If I wanted to figure it out for like A equaled 9, I'd have to redo it and find out where the tangent line is over at 9 in order to get a new line to use as an approximation. So we're always doing it based on something close to a particular number. Now, the very first thing we have to deal with in this is, notice I have not yet given you the A value, because I want you to really think through what I can use this equation for. So notice these are the values that we're going to be estimating, 3.9 and 4.1. If those are the values I want to take the square root of, what should I plug in for x?
0.
It's not 4 this time, because 4 plus 4 would give me 8. That would be estimating the square root of 8.
12. 12.
0.
We want to do 0. Because I want the number inside here to be close to these two numbers. Well, both of those are close to 4, so I want the number inside to be close to 4. That means a is going to be 0 in this case. All right. Now, in order to do this one, again, the very first thing we want to do is we want to find our derivative. Specifically, we want to find g prime of 0 here, because it's always of our a value. So take a moment, please find this derivative and plug in 0 and see what we get. So as we go and work this one through, again, remember that it's x plus 4 to the power of 1/2. So when I go to find that derivative, I can use power rule again, so it ends up being 1/2 times x plus 4 to the power of a negative 1/2. But remember, we have to use chain rule here, because it's not just an x on the inside. So I need to multiply that by the derivative of the inner function. That's the x plus 4. What is the derivative of x plus 4? 1. And so I can write in that times 1, but of course multiplying by 1 doesn't change what it is. And so this derivative, yes, make sure you remember to use chain rule, because there are conditions where it will change it. But in this case, it looks a whole lot like the previous one we did. 1 over 2 root x plus 4. And then if I want to know what g prime of 0 is, I plug the 0 in for x. And so we end up doing 1 over 2 root 4. Looks just like the last one now, of course. And 1 over 2 root 4 is 1 over 4. So we know that our derivative is 1/4, yet again. Okay, please find b. And I'm going to give you a little hint here. It's not 1. Now remember, in order to do that, you do have to know what your original function is. So you want to do g of 4, so you know what your y value is. I'm sorry, not 4.
0.
Yeah, I get 4 on the brain. G of 0. So when you do that, of course, the square root of 4 ends up giving us 2. So that's the y value that you should be using for finding your equation, for finding your b value now. And so when we plug in the x and y coordinates, I can then go ahead and solve it for b. Notice 1/4 of 0, of course, is 0, so we end up getting 2 equals b. Now that I know that b equals 2, I now know my equation, because I can just plug that 2 value in for b. So I now know what L of x equals. L of x, remember, is a way of estimating the value of my original function at values close to my a value. So I can use this for finding numbers that are close to 0. And yet, I want to figure out the square root of 3.9 and the square root of 4.1. We don't have a conflict here. Let's see why. If you want to be using this equation to figure out the value of the square root of 3.9, what is x? What are you plugging in for x that would equal 3.9? Well, what plus 4 equals 3.9? Yeah, negative 0.1. And so notice, in this case, it ends up feeling a little different. We actually have to figure out, okay, how far away is it? It's like, another way to think about this that for some people makes it easier is, instead of thinking about it as x, you could actually think about it as delta x. How far away is that? Those of you who have a history of using delta x a lot, that might feel more comfortable. If not, don't worry about it. We just want to know what's going to make this into this. And so for that one, what plus 4 is 4.1, that would be a positive point. And so go ahead and use those two x values now. Estimate our two square roots using this method. And so to work this out, I plug in the negative 0.1 over there. And I got to do now 1/4 times negative 0.1. What is 1/4 of 0.1?
Negative 0.025.
In this case, negative 0.025. What is easier to do without a calculator? Is it easier to do 3.9 divided by 4 or 0.1 divided by 4?
0.1.
the 0.1.
Say that.
And so by using this method instead, we just were able to break this down into something that's a lot easier to do without a calculator, because we're now doing it of just like 0.1 divided by 4. And so then this gives me 1.975. Yes, it gives us the same number. In fact, the other one will give us the same number as well, 2.025. We get the same results out, but the point of this is being able to do it without having to rely on a calculator at times, especially for functions that get really crazy and complex. And so you'll notice that by using this equation with the plus 4 inside, our math got to be a lot easier. Now, it did mean that we had to think about it slightly differently, right? But it means that the numbers are much more reasonable to work with as we go. They both have their pros and cons, and so both are going to come up. And so you need to be able to use either way. Now, you'll notice that when we did this one, we got the same slope. That's good, because that means that at this same value, where we are approaching 3.9 and 4.1, the tangent line was going up by the same rate. Basically, if we take it back to the graph again, you'll notice this time we are finding a of 0. You notice the graph looks very much the same, except that our graph was shifted left 4. Well, if I draw on the tangent line, but at this time it's 0, and then zoom in on it, you'll notice again, we're getting those really close values. It's the same line against the same curve, it's all just been moved over. So, looking at this problem, you notice once again, the first thing I'm asking you to figure out is what would A be? What would be a good A to use, knowing that these are the estimates we're going to be making?
0.75.
Yep, I want this number to be close to, looks like 1. Well, that means that x should be 0. So hopefully you are then looking for the equation of the tangent line to this curve at 0. All right, and then check that you did the derivative correctly. Then once you get your derivative, we plug 0 in, and you should be getting a slope then of 1/3. All right, and then you're going to go ahead and find your b value. Now remember, to find your b value, you got to plug in your slope, which we just found, and an x and y coordinate pair. Well, we know x is 0 here, because that's what we found for our a. And so if I plug that in, 1 plus 0, of course, is 1. The cube root of 1 is 1. So the y coordinate you're using is 1. All right, then you should then, after you plug in the coordinates in our slope, you should find that our y-intercept is at 1. So this is our equation of our tangent line. And remember, because it's actually a linearization, we're using the formal notation of L of x now, equals 1/3 x plus 1. And now that we have that, use that to approximate our two cube roots. So when you go and do this, the very first thing you have to do is know what are you plugging in for x for each estimate. So for this first one here, what do I need to plug in for x in order to make this equal 0.95? It'd be a negative 0.05, yeah. So for this first one, you're using negative 0.05. And for the 1.1, what does x need to be there?
0.1.
Yep, 0.1 on that one. So those are the numbers you're now plugging in for x. But again, we won't be able to do this without a calculator, right? Well, if I plug that in there, so I'm going to do L of a negative 0.05 equals 1/3 of that. Now, when you're doing 1/3 of a negative 0.05, we might have to rely on a calculator there unless we're pretty clever, right?
I know what to do, Mr. William.
Well, there is one way around it, which you have the option of doing here. Now, you can go ahead and calculate it. You can go ahead and break out the calculator for this. But there is another option. Actually, I'm just going to write it here. What is 0.05 as a fraction?
So 500.
It's 5 over 100, which is 1/20th. So if you want to with these, you can actually turn them into fractions and you can live in the world of fractions. And so this would equal 59
It's a good world to live
60ths.
Oh, maybe.
All right, now for that last one, we're going by 0.1. Now 0.1 is 1/10. So if you're choosing the fraction route, then you do 1/3 times 1/10 plus 1, so that's 1/30th plus 1. And so it's 31/30ths, or 1 1/30th. If you got it as a decimal, of course, you could do 31 divided by 30 to get a decimal at this point too. That's also fine. And then once again, just to again picture what we're actually finding here, you'll notice at this particular point on the graph where we were looking for it, you'll notice when I get really close to that graph, it is looking straight. That tangent line is almost indistinguishable from our curve for quite a ways around there, for almost like a half. It looks like a really good estimate from this particular zoom level at least. And we'll get into a little bit later about levels of accuracy and how close do we need to be and some stuff like that. But remember why this works, because I just want you to actually remember why we can do this is a matter of that tangent line is just really, really close to the curve if we're really close to the initial point where it was found. All right, now knowing that, we can now use our skills that we've seen today to approximate a value which otherwise might just seem kind of silly to be able to find by hand. Please find this value, though, without a calculator. So the interesting thing is that a lot of you are just like, nope. But you aren't thinking about, you actually know how to do this. Because like, I want to be able to find something that's close to this. Now, what's a number that's close to 0.03 that's easy to find something like sine of? 0. So we're going to be using an a value here of 0. Okay. I want to start by finding the equation of the tangent line at 0 then. Well, step 1 is find the derivative. Notice this would be the derivative of sine of x. What's the derivative of sine of x? Cosine. And so my derivative is cosine. So what's cosine of 0 equal?
1.
Well, actually think it through. Know your unit circle. So again, you should be able to visualize, unit circle.
And 0 is
Cosine is how far we're going over. So yes, cosine is 1. So cosine of 0 is 1.
Why did you say that?
Why didn't you sniper cross there?
Okay.
I knew it was 1.
Now that we know that, that's our slope. Now we want to write the equation of the line. Remember, L of x, our linear approximation equation, equals mx plus b. We know what m is now, right? So I plug that in for m. Well, of course, 1x is just equal to x. So I know that L of x equals x plus b. Okay. Now we need to plug in points. What's our x value here that we're using? 0. Plus b. Now I need to know is what's the y coordinate? Well, if y equals sine of x, what would y equal if it is sine of 0?
0.
Yeah, sine of 0 is 0. And so I could plug that 0 in over here. So what does b equal?
0.
So then what does L of x equal?
X.
X. Because it's 1x plus 0. Of course, 1x plus 0 is just x. The whole linearization equation is x. So, remember,
So that just is.
I'm looking for the value at 0.03. Well, I was looking for close to 0, so I don't need to do anything funky to the 0.03. It is 0.03. So what is L of 0.03? And there you have a quick estimate of sine of 0.03. So then, why would we want to know this? Why do we want to do all that work just for that one value? Well, usually we're going to be using this in terms of, and where it actually gets applied is when it's not just one value? What if we're looking at, hey, around 0 here, let's find a whole bunch of sine values. What's the approximate value of sine of 0.1? It'd be about 0.1. What's the approximate value of sine of pi over 100? Pi over 100. You notice we can know a lot of values now very, very fast. And so while we're only doing like one value with each of these, we could actually roll it out where I could give you like 10 different values to find, and they would all be super easy to find. I'm just not having you go through all that work because it becomes repetitive, right? But we can use this L of x equation that we've found to go find other stuff very, very fast, instead of having to do it the much longer way.